What are we going to cover today? I have things I need to do in the lab. I have been kept from my lab all week, and I'm very needy to get to get in and actually just do some stuff that would be fun. And there's a number of things on my mind here. So if I got a bunch of different projects. One is understanding 4-byte autonomous system numbers for BGP, which is not at all hard. It's just one little thing that I ran into that, yeah, I thought was a fun detail to go over, especially if you're building out labs. If you're used to just like, oh, I'll do 65, whatever the number is, I know those are private AS numbers. Well, you can do 4-byte autonomous system numbers nowadays that are a lot longer, and you can do private ones of those too. And I thought we'd take a look at that in the lab since I stood up a few routers and have a sense of what that looks like. It's kind of fun, actually. There's a little bit of binary to decimal conversions and so on. And then there's a bunch of other things that I'm going to get into. So if I bring up my Feedly, what I've started doing is saving off a lab section. And that lab section has got a bunch of different things I'm interested in doing. So, for example, the guys at Network Decode, they're a company that specializes in network automation. They work with your business, they figure out your workflow processes, and then put a network automation system in place for you, along with teaching and training and whatever all else they do over there at Network Decode. There was a great little article here backing up device configurations using Nornir and Ansible, which doesn't mean you're backing them both up. Doesn't mean you need both tools to accomplish a backup. It's actually a compare and contrast. What if you want to use Nornir to do it? What if you want to use Ansible to do it? It's like, oh, I thought that'd be a fun lab exercise to do at one point. This thing about Bugman is actually not technical. It's just a description of our society as a whole that I don't want to talk about today, but I do want to talk about at some point. Monitoring your network using OSPF. Well, Flock Networks is a bit of a startup where the guy that's running it has been rewriting network protocols in Rust for performance reasons and wants them to be simple, these protocols to be simple and predictable to implement. And I've been wanting to play with that. So I should be able to stand up a Flock Networks OSPF instance on a Linux box, peer it up with a virtual router somewhere else, and just exchange some routes. I thought that might be entertaining. Python objects. Here's a topic that we can talk about someday. If you're new to programming and scripting and have never worked with Python or any object-oriented language, I thought this article, another Network Decode piece, was a great way to begin to understand what you're looking at here as you begin to see classes and objects, and then how to get certain data out of a Python object, what's really going on in there. And then using the Python code formatter called Black, which is inspired by Henry Ford's Model T notion that you could have any Model T color you wanted as long as it was black. And that was one of the ways he was more efficient as he did his manufacturing of automobiles. That was the whole thing. And the idea behind Black, the Python code formatter, is you can have your code to be formatted any way you like it, as long as it's the way Black does it. So when you get into Python scripting, the whole idea there is a standard convention for how you need to format that code so that it's readable. So things like indentation and white space and so on all matter, and Black will format that for you if you want. So anyway, these are ideas I have for lab stuff going forward that, just fire up the live stream and start bashing around and see what happens. Today, I wanted to cover something fairly simple here. 4-byte autonomous system numbers. So with BGP, you traditionally had a 2-byte autonomous system number. And there's an article here that I've got up in the browser that you can see by Jeff Doyle. Jeff, if you're not familiar, wrote a couple of, well, he's written several books but two of them on TCP/IP and routing protocols that are considered kind of standards in the networking industry. So this article goes back 12 years, 2008. So it's not like 4-byte autonomous system numbers are new, but Jeff is someone that you can look at as an author who really knows his stuff when it comes to technology, IP, and IP routing particularly. So this article covers a lot of what was going on. And if you go back to 2008, well, what happened here? You had this 2-byte, a 16-bit number space giving you AS numbers 0 through 65535. And if you've done any BGP provisioning, you're probably really familiar with that. And some of them are reserved to be for private use. The IANA reserves 1,026 of these, basically the upper end of the range, 64,512 to 65,534 for private reusable ASNs, like you would do in a lab or kind of like you might do for RFC 1918 address space. Why use a public autonomous system number that would be meaningful to the internet if it's just for your internal use and you don't need to share those in any way? Okay, there's a few other notes here like 2, 3, 4, 5, 6, special use and so on. And as we scroll down through the piece, Jeff points out that 4-byte autonomous system numbers, we just doubled the number of bits. We went from 16 bits to 32 bits, or 4 bytes. Now we've got 4,294,967,296 autonomous system numbers, etc. And you still have a private range here. And what gets interesting about this is simply, how the heck do you remember a number that is so large, 4,200,000,000 and whatever? You can't keep that in your head. You keep a 5-digit number in your head pretty okay. Back when we were at a 2-byte ASN number and you were limited to 65,000 and something on the top end, you could probably remember that one. 4 billion and something? No. For the same reason. I mean, do you remember phone numbers? No, you keep them on your phone, right? You got a contact list there that abstracts that away from you. You can barely remember people's names if you're my age, let alone some obscure number like that. So, all right. That leads us to, well, how then do you represent these 4-byte autonomous system numbers? You could just use the raw number. But you've got a couple of other options here. Just the raw number would be a method called AS-plain. AS-plain is a simple decimal representation of the ASN from 0 to 4 billion whatever. But you can split that number in half across the byte boundary. It's just so 2 bytes on the left half and 2 bytes on the right half. And then use this second note here that Jeff mentions in the article, asdot plus, breaking up the number order from low order and high order 16-bit values separated by a dot. So instead of just 65,000 whatever, you could have 65,000 whatever dot 65,000 whatever. So two 16-bit numbers in effect representing what is really one very large 32-bit number. Now there's another here, asdot, that I actually haven't seen in production, but it is a mixture of AS-plain and AS-dot plus. Any ASN in the 2-byte range of 0 to 65,535 is written in AS-plain, and any ASN above that is written in AS-dot plus, so that 65,535 is written in 1.0. So you don't see that a whole lot, and Jeff actually mentions that here. If we scroll down to this paragraph, AS-dot might appear to have limited usefulness. It's not any harder to write. There is a subtlety to this, as he points out. The regional number assignment authorities, the REERs, differentiate 16-bit and older 2-byte ASNs and a mappable 4-byte ASN. In other words, you had a 16-bit and you want to map it to a 32-bit or 4-byte in that way. So now the rest of this article happens to go into a lot of issues dealing with the REERs and so on. And for our purposes and the rest of this lab, we are not going to go through that. What I wanted to point out is some of the RFCs that deal with this topic, so you get more authority here, and then pop into the lab and have a look at what 4-byte ASN numbers actually look like. So we got one document here, the textual representation of autonomous system numbers, a scintillating title, no doubt, RFC number 5396. Let's open this guy up here a bit, Oh, my expand zoom is not working. So let me kick this back in. There, that should be more readable for you. Abstract. If you're not familiar with reading IETF RFC documents, okay, IETF, Internet Engineering Task Force, the RFC, a request for comments documents. These are documents that by the time they hit the RFC stage and are published means that they have gone through an official vetting by the industry, let's put it that way, where vendors and customers and service providers that are all critically interested in the internet doing what it does and have a say in new standards that come along have had input into these documents, and they go through lots and lots of revisions via IETF in-person meetings and on mailing lists to finally be handed down from on high the tablets that are the RFC documents. These are references for you as a network engineer. If you're not using them, if you don't know what they are, get familiar. They are typically readable and understandable, but also pedantic and obscure depending on just what level of detail you're trying to go into. So if you look at the abstract that is at a lot of the top of these, you should always read that abstract section in the RFC because it gives you a lot of insight into what this document is all about. It gives you background and context. Now, this is an older RFC, right, 2008. It's far, far from the oldest, but it's got some years on it, so you might be like, I don't care about this, right? It's old. Well, you do. Let me take us back out of reader mode here. If this document had been outdated or replaced, there'd be a note here in the header of the document that says this RFC has been updated by, and then they would provide a link to a new RFC. So this is still relevant even though it's as old as it is, which makes sense. 4-byte ASN numbers is not one of those topics where you'd think, oh, it's so complex and there's so much nuance, it's just likely to be changed and updated all the time. Not really. So what are we talking about here in the abstract? A textual representation of autonomous system numbers defined as the decimal value of the AS number. It is to be used in all document systems and user interfaces referring to AS numbers. In other words, you're going to find this logic everywhere. We don't need to go through it too much. I just wanted to tag that information that Jeff shared in that Network World article I pointed out to you earlier is documented here. AS plain, AS dot plus, and AS dot. Those are the key reference here. Again, AS plain, just a simple decimal representation of the AS number. AS dot, the separation of the 32-bit 4-byte ASN number into two 16-bit chunks, so you get two decimals separated by a dot in that representation. And then the AS dot, not AS dot plus, but just AS dot, giving you, well, let's just read it here. A syntax scheme representing AS number values less than 65,535 using AS plain notation and representing AS numbers greater than or equal to 65,536 using AS dot plus. And then you're separating these up and getting a subtle notation of giving you reverse mapping, as Jeff put it, so that you can look at older numbers that would only be relevant in 2-byte in a 4-byte notation scheme, which again, I think to us doesn't matter a whole lot. All right, another RFC here, take us out of reader mode, autonomous system reservation for private use. So this would be a document that is in parallel to the RFC, where's the number here? 5396. This one is 6996 from July 2013. These are ASNs that you can use for, again, private use behind your firewall, not exposed to the public internet, in your lab, and so on. And hey, I'm working in a lab environment, so this matters to me personally. I'm curious to know what the IETF says I can use for private ASN numbers. That seems to be a best practice. You know, what would happen if I just picked some arbitrary ASN that was actually in use on the public internet and maybe somehow I set up a BGP peering accidentally from my lab to the public internet? I mean, how would I do that accidentally, right? But, you know, things happen, so you play by the rules, you do what you're supposed to do. You do what you're supposed to do. So the original ANA was for 1,023 ASNs, and this was documented. And then RFC 6793 talks about 4-octet autonomous system numbers. Oh, I didn't even bring up that one in this in my set of tab collections here. And so now they're basically saying, hey, we're updating this document because things have changed in the world of BGP. Because by golly, we have 4-byte ASNs now. Oh, very good. So what is the range? We got more boilerplate and background. They're telling us many things that we might see in the AS path characteristics of the BGP AS path when we were to look at BGP routes. Skipping. Let's get to the meat of this. We want to know our numbers. IANA has reserved for private use a contiguous block of 1023. This is the same as it ever was, 64.512 to 65.534 inclusive. So that's from the 2-byte system. If we extend this up into the 4-byte system, IANA has also reserved for private use a contiguous block of 94,967,295 autonomous system numbers from the 32-bit autonomous system numbers registry, namely 4.24, yeah, that's 4,200,000,000, there we go, to 4,294, blah, 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 inclusive. So there's our ranges. You got it, 64.512, 65.534, and then 4,200,000,000 all the way up to the top of the range there, very close. Those are our numbers. Alrighty, so now this gets interesting as we talk about routes and route notation here. So here I've got a small little network that I've got. I'm actually going to show you a GNS3 lab topology that will be a little overwhelming. Take a deep breath, it's okay. We're only dealing with 4 routers here, the ones that I've started. This is, this whole topology you're looking at is part of a much larger project that I'm working on, which you'll also get some live streams of. It's an imaginary company called Behemoth Bikes, and they've got offices in different places, and they got a bunch of problems and business problems and concerns, and if you begin looking at this topology, you can just infer what some of these problems are. But that's not what we're worried about today. I'm just using some of the WAN routers from Behemoth Bikes so we can talk about it. We got a router in Boston, a router in Los Angeles, a router in Denver, and then a core service provider router. It's not meant to actually be seen by, Behemoth Bikes. You'd never see this if you ran this company. But I needed some kind of a device to glue all the remote offices together. So it's my service provider router. And for our purposes, that's the part of the topology that we care about is these 4 routers here. Let me zoom in on this for you and see if I can kind of filter down a little bit of the noise. So there you go. How's that? Ignore some of the text and just look at these 4 routers here. And you can see this is very simple. We got SP, service provider router, one in the middle, and think of them as our hub. And then we've got Boston, Denver, and LA as spoke routers hanging off. And they're all paired together with BGP. So as we look then at the router configuration, we've got some BGP peering that has been established. I've already set this up for us. So if I say show BGP neighbors, let's see, I might have to do BGP neighbor. There we go. Oh, I got more information that I want here. Hang on. Brief. I just want the short neighbor list. Ha! So let's summarize this. I thought there was a brief here, and obviously I haven't worked at this. I set this lab up a couple weeks ago. I haven't gotten back to it yet, so I've forgotten some of the rote commands I would need off the top of my head here. That's fine. Oh, that's still more than I want. Let's tighten this up. I can say include BGP neighbor. There we go. Oh, that's even And that's tighter than I want. Well, you get the idea. I've got 4 neighbors set up here, 1034, 127. Do I have 4? Hang on. I love live labs. Oh yeah, I do have 4. That's one I forgot about. Hang on. I love live. Although I didn't even start that router, so that's interesting. Why does he think that... Ooh, this will be fun. Now I got another place to go here. So if I go... Right. So he thinks, my service provider router is the he here, thinks that he's got a neighbor adjacency up to a Colo WAN router in Chicago, and I didn't even start that router. So fascinating. What is going on there? That's the 10.41.80 block. Does that add up, or am I forgetting something here? 9.253. I love doing live stuff. This is awesome. 80. And Boston, right, it's the 79. So that should be that would be my 95 router, the way I address these, because I put the router WAN interfaces into the top of the subnet ranges I assigned to each of the offices. So this should be 10.41.95. Okay, so that's the neighbor. Okay. Wow, this is fun. So if I show and we look at the section router BGP, we'll get all my neighbors to be shown here. All they're listed. And what the heck, let's start that GNS3 router. The Chicago router in my GNS3 topology, and bring that guy up, because let's do that. That'll deal with some confusion. Custom console, I'm using Zoc 7. Boom. All right, that guy's starting up. We'll let him start up. But I do want to point out a few things here in this router BGP configuration. First of all, I'm using this command here. It says BGP AS notation dot. So I got router BGP, I've got the autonomous system numbered. It is in 4-byte notation. I've got the command telling this device, this router, that I want to use dot notation. Well, what are my other options? Well, let's check that out. So if I go and I say BGP, AS notation, what are my choices? So I've got dot, AS dot, or just plain old notation. Oh, I can only say, that's the descriptor field. That's not giving me multiple options. I see what they're doing there. So I have one choice. I can turn on dot notation, or I can turn it off. So if I say no BGP, AS notation, dot, and then we look at our router BGP segment again, section of the configuration again, what do we see? Well, before we had that dotted notation, right? Now we've just got one big ugly decimal number for these private ranges that I've assigned to everybody. And it's the same thing if I look at my BGP paths that are in this topology. What is my path? Well, my path shows, like for that first network, 10.34.112.0/20, my next hop shows that next hop router, and then a path of for 201.095.330 by this big long private 4-byte AS number. So if I go back in, so this will be interesting. So I turned off ASdot notation, right? And I'm just using plain decimal notation now. Well, this was the AS number of this router in ASdot notation. So if I use that when I don't have the feature enabled, what happens? Let's find out. Oop, didn't bark at me, didn't complain. Okay. So now I can say, what was it, dot notation? No, I don't remember. AS notation, BGP, AS notation, and then dot is my choice. If I show BGP again, there's my path. Oh, I got a new route in because that Chicago router is up and running now and advertising. Now I'm seeing that big long number split into, that big long 32-bit number split into, as they were saying, high order and low order 16-bit. The high order are the ones in the beginning and the low order are the ones at the end of the 32-bit list. I think that's all that we're meaning there, okay? So we split that number in half, taken the first 16 binary bits and converted them into this decimal number. And then we've taken the second group of 16 bits and converted them into a decimal number, then split them with a dot in the middle. Conveniently, there is an online conversion tool for this put out by Apnic that I found out. So if you look at the URL here, submit.apnic.net CGI bin, old school. They have a convertasn.pl, which must be Perl, right? Okay. Wow. Okay, but this tool's been around for a while. Sweet. I feel at home. So let's pick on some numbers here. I'm going to take 64.103.41122. Let's copy that. Paste that in and let's say convert. What's it give me? Thinking, it's thinking. There we go, the converted ASN for that goes down to the decimal for 201.095.330. Not hard to understand. And we can also go the other way with this tool. So let's do this. Oh, it's going to make me remember. I don't remember what it was. Even decimals are hard. Okay, there it is. No, BGP AS notation dot. I'm going to do a show BGP. And okay, let's focus on this 10.34.112/20 route. I've got that number there. 4 billion, lot of numbers. Pop that into Apnic's converter. I say convert. It thinks, the Perl engine grinds up. It begins to think very hard about this. There's an abacus involved. And then, finally, we have a conversion, 64.103.41122. Right. So I'm going to scroll back up to when we did the show BGP before. We had turned ASdot notation back off, and 64.103.41122. It's a match. So anyway, that's, I didn't expect it to not work, but I just thought it was a nice little tool that to have on there, and not especially complicated. So again, what does this look like if you were to do this by hand? Well, let me put you on the whiteboard here. I want to do that one and that one. All right, let me bring the my whiteboard into screen for you. can still see that. That looks good. Okay. So with, let's clear up some of the paper here. Apparently I've been using this for things. I'm using this for a lot of things. Oh, a lot of diagrams on here. All right. So if we have originally a 2-byte autonomous system number. That means we've got 16 bits. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we got, that's what we had. Now we've got twice that many, so we're splitting that up. So this is a byte. And that's a byte. And this range here of up to 16 numbers, this would give us that, if we were to do a decimal to binary conversion or binary to decimal conversion, we would end up with as much as 65,535 would be our range. So now if we go to a 4-byte ASN, now we've got 16. So this is a lot of zeros. Hang on. We got two groups of 16 bits for a total of 32. That's a byte. And that's a byte. And that's a byte. Oh, and I fit it all in, and that's a byte. So with, so here's, that's a byte, a byte, a byte, and a byte. AS plane is going to take this entire huge number and represent that as a decimal all by itself. All right. AS dot takes two 16-byte numbers and then separates them with a dot here. And that's it. It's all the magic. That's all the magic. I don't know how well that's showing up on the screen there. I probably need yet another camera that I could zoom in on that. But you pretend you're in the classroom and you're looking towards the front. You're looking at what the crazy person out there is scribbling onto the board. And that's 4-byte ASNs in a nutshell. So let's look at some Cisco documentation here just to fill in the final bit of blanking that you might have on this. So I have pulled up BGP configuration guide for iOS release 15 M and T. There's a lot of BGP docs that are in here. If you go higher up and get more granular, I want the docs for 15.7. You might not find them. You gotta go to the base documentation route. And this configuration guide for BGP, this is where I found most of the BGP stuff that was interesting in this M&T release. So if I click through to this fifth entry down, BGP support for 4-byte ASN, it loads up and talks about a lot of the stuff that we were talking about here. And what have we got? Well, it just basically tells us a lot of the same things that we know. AS plane number formatting and what that looks like. AS dot number formatting and what that looks like and how to do the conversions. And notice here with the, if you go to AS dot, they bring in that AS dot and AS dot plus. They're using, Cisco here is using both of those all encompassed in their definition of AS dot notation. They also note in here reserved and private AS numbers, and then the Cisco implementation of, and then they talk through exactly how they are doing the implementation, what the steps are. And I'm actually looking for the commands where they show this, as they talk about this is like standard BGP configuration stuff. They don't actually mention how to change the notation in this section of the doc. Okay, there we go. So modifying the default output and regex match format for 4-byte ASN numbers. And here they show BGP AS notation dot, that one command that we were looking at in the router configuration. And then no BGP AS notation dot, which is how we shut it off. Those are the only commands that are in there related to this topic that I can see. It's also worth noting, if you're an operator, at least in the version of iOS code that I'm using, changing asdot notation was strictly local and interesting to the router only. That is, when I made the change, we didn't have any BGP neighbor resets. We didn't reload routes. Nothing happened to my forwarding plane on this router. It just changed the way the number is represented if I am at the command line looking at the console. So one last time, I'm going to go to, whoops. I still don't know what that is. Okay, router BGP. BGP, AS notation. Whoops, dot. There we go. Exit, exit. And we can see the notations change. There's nothing changed about the routes. If I look at my IPv4 routing table, the routes have plenty of age to them from when I first brought these up, including that router I brought up later, which is from Chicago. You might remember he's only 11 minutes old because it took me, I didn't bring up that router until later because I forgot about him in my lab topology. Again, we got no neighbor resets or anything like that, so this is should be as risk-free as anything is in iOS. Your mileage may vary. If you turn on BGP AS dot notation and your router crashes, well, Cisco code, what can I tell you? It's what it is. Not the kind of thing that's likely to happen, but, take no chances.